example, I will go here, for example, is can we, if you know the network of the power grid in Europe, we can improve the power grid significantly to random failure. For example, if you have the current power grid, the current power grid is a phase like this. This is the amount of failures, random failures that I give to the network. So if I go in the current power grid, I can go down. It goes to about 20% if I remove about 10% of the nodes randomly. However, if I do some changes in the network, very minor changes, I can make it to fail only to 60%. It means instead of 20% we get current, we get electricity, it will be 60%. So we can improve very much the structure of the network to any failures that you like. The same is for the internet. I will show you two more examples just because of short of time, but there are many, many examples. Another example by network, if you take a network that the green points are the brain and the other are physiological systems, you can see that there is a link between the brain and other physiological system and between the other physiological system like the eye, like heart rate, like respiration, and you can see the following phenomena. If you go during deep sleep, you can see here that only the brain interacts with itself in deep sleep. However, when you go to light sleep, every physiological system speaks to another one. There is interaction between them. And this, I think, is a new phenomena that was found only due to network analysis and explain what is the difference between deep sleep and light sleep. Although people, I mean, the medical doctors can distinguish between them, but they did not know that there is such a big difference between the behavior of the interaction between physiological systems during deep sleep. Only the brain, it means deep sleep you rest, not any interaction with other systems, but when you are in light sleep, you see the network of physiological systems, they interact with each other. Another way is to study, for example, the key player in a network. They are not just those that have high degree and one can find the key player. It's very important. The key players are important also for pandemic. For pandemic, we want to know who are the ones that are most, they spread the disease. They are super spreaders, and you can find it by this phenomena, by this method that we found in 2015 it was. So we have a lot of successful research on signal network and like predicting epidemics, like efficient immunization strategies, climate, El Nino, what I told you, identifying key players, physiology, as I showed you, robustness of networks. We have also very nice, very useful results for traffic, to understand traffic in a city, protein network function, and many, many others. So the question, if we can use a single network for so many phenomena, why do we need network of network? And this is what I'm going to try to explain you. So why do we need network or network? You can see in the picture here, it was in the news in 14 March 2011. And you remember it was the blackout and the tsunami in Japan that led to cascading failures to all infrastructures could not function. The transportation, the electricity, everything led to other failures. Like I told you before, that you can have a cascading between systems. And so this is our motivation, because you can have cascading between systems. One system doesn't function, it leads to another system, and the other system leads to another one, and it can give a feedback also to the first system. Now, this question is not new. This question was already in almost 19 years ago was known to engineers, and the engineer is Rinaldi from Florence, and he wrote an article, How Interdependent Are Infrastructures? And he showed that power grid depends on natural gas, depends on transportation, but not only it depends on everyone. Everyone depends almost on everyone in the system. You need water, you need telecom, and they are interacting and depend on each other. So the concept of dependency was known in the engineering literature a lot, but there was no model. like a systematic model that can explain and can understand the phenomena of cascading failure due to dependencies until 2010 with the paper Nature that we published. Another example of motivation is in Italy, where there was a blackout in Italy in September 28, 2003, where failures in the power grid led to failure in the communication system that controlled the power grid, the SCADA. And this was studied by Rosato in 2008, and he found that there was cascading, there were failure here, led to failure here, and back to failures here. And then not only this system failed, the railway did not work, the healthcare system didn't work, and financial services, communication, it was a day without any net functioning infrastructure. So to understand this, and also the body, you know, our body is also a system of systems. So if one system doesn't function, the heart, for example, or respiratory or a brain, it led to cascading to other systems and it can lead to system collapse. So we need to understand, to have a method, to have a systematic method, a mathematical method to study how a system collapse. And this, our system of system can have cascading failure, and the failure can lead to fully collapse of the system of systems. So I will give you the summary here of my talk, and then I will be more specific on every step here. So first, I will show you that cascading failures can lead to abrupt collapse. It means if I have cascading failures in one system, it may lead to another system failure, because if this node fail, it leads to this node fail, and it can lead to another node failure in this system. And if this fail also, it fails this one, and many nodes can fail, and can have a feedback. How can we study this using analytical tools, a framework from mathematics or physics? So this is the first step that I will speak. The second step, I will show you that we studied until 2010, from 1960, it means for 50 years, percolation theory for one system. It means we have a system and we had failures and we could see what is the functional network that is left due to these failures. And I will show you it's a very natural generalization of percolation to network of networks. Instead of studying one single system, we can study network with the same tool. It means what we studied was only a specific case of single network. But when you have network of networks that depend on each other, the formulation is more general, and it includes as a specific case the single network. This is what I will show in a second, and then I will go to the last one, which is very important also, is a new type of failures, which we call localized attack in spatial network of networks. Usually infrastructures are in space, not only infrastructure in space. For example, the brain network is also in space, in 3-dimensional space. Infrastructure is usually in 2-dimensional space, like the transportation system. And now the percolation becomes very different. A localized attack in a certain area, or almost in any area of a certain size, leads to enough cascading failure can lead to abrupt collapse. It means localized attack means that I have, even if the system is infinite, and I take a zero fraction of the nodes, it can lead to abrupt collapse, because the failure, the localized failure, can spread in the system because of the dependency. And this is actually what happens in many cases in blackouts. So let me go first step by step and show you first the cascading lead to abrupt collapse. And first, let me explain you again what happens when you have just percolation of a single network. So we have now, already for many years, we have many types of network, but let's look on two typical type of network. One we call exponentially, or the Erdős-Rényi network, which is known, to be, oh, sorry, I lost it. What happened now? 1 second. 1 second. Okay, now you can see it. So we have two types of networks. In both networks, when we have random failure, the component that still function, that can connect to each other, is going down. When P is 1, it means everyone is connected. But when P is 0.8, for example, 20% of nodes, fraction of 20% failed randomly here and here. We have here how the giant component, the network component, as a function of P, of the number of functioning nodes, behave. And we can see here in the Erdős-Rényi, in the exponential one, it goes down to 0 and at a certain critical point. In the scale-free, which is the one that we found in 2000, that is more characteristic of real network, PC goes to 0. It means you have to remove almost all nodes until the system collapses. And this is also comes because of the reason that in scale-free, the difference between exponential or between Erdős-Rényi and scale-free, that Erdős-Rényi, the number of links per node decays exponentially. And because it decays exponentially, you don't have a high degree nodes which have many links. You can see here you have typically you have 2, 3, but not one that have 10 or 20 or 30, because this Poisson leads to a certain typical number of links per node. However, for scale free, which is more realistic, we can have hubs. Hubs means that nodes that have many links. And you can see here they have many links. Here you see many links. These are the red. So the reason why for scale-free PC is 0 comes from the fact that if you remove randomly, usually you remove the low-degree nodes because they are more frequent because of the power law, in the case power law. And then the hubs, they still connect the system. And only when you remove many nodes, or even all of them, then you start to see there is no giant component. And why it's not linearly? Because when I remove nodes? Because when I remove nodes, it's not only that the nodes are removed, but also some small clusters are removed. And that's why it's not linear, it goes down, not linear, and they have a phase transition. This is actually a phase transition. Now, this is the story for one, and you can see a continuous function, which was already in 1960. It means 60 years ago was this developed by Erdős-Rényi, and in 2000 we developed a similar formula, analog formula for scale free. We know exactly what happens for a certain failure, a fraction of failure. So, but you can see that this is continuous. It means that if I remove a little more, the network is smaller, but not going to 0. However, when we have now, instead of having the continuous transition, now I look on this system. If I have interdependent network that depends on each other, and here you see these are two Erdős-Rényi, two type of this network are connected, but they are connected by red links. It means that if this node fails, this node also fails. You see, this is one directional of dependency, and the vice versa, it doesn't work. But here it's both direction. But it doesn't matter, even if it's one direction, or if it's two direction, you have a new phenomena which leads to cascading failure. And this cascading failure shows that instead of having a continuous transition, it means that less and less nodes can communicate in the network, like in a single network. You have a point at which one more node, if you remove this point, another critical point, if you remove one more node, there is enough cascading failure which lead to abrupt collapse and the system collapse. This is a new paradigm that we have abrupt transition paradigm in mathematics, in physics. We can show it analytically, and you will see soon that you have this abrupt collapse at PC. And the message is because of the dependency. And you know, the modern world makes more and more dependency in our world. And because of the dependency of one system to another, 20 years ago, when we wanted to make a phone call, we can use the phone easily. We didn't have internet. Today, if you don't have internet, usually, if you don't at home, you don't have internet, usually your phone does not function also. So the system becomes more dependent because of the technology, because of the modern technology. And because of this dependency, we can get abrupt collapse. One system failures lead to another system, and like in our body also. So the message is our world is extremely unsafe, because if the manager of the power station is here, for example, he knows if there is one more failure, it doesn't know, but it can be one more failure can lead to abrupt collapse, and the system fully will collapse and nobody will have electricity in the system. And this is what happens in power grid systems. So now we have also, I will show you the theory for this also, and the theory we do by generalizing percolation to network on network. Now we don't have only percolation of a single network like here. We don't have this formula on for this. We ask ourselves if you have two Erdős-Rényi, or even more than two. You can have 3, 4, 5 systems or scale free. What happens? Like this. Failures in one system will lead to failures in another. Can we see this phenomena by percolation theory? And indeed, we can see it. And I will show you a simple example that will convince you that we can see it. So what is this example? Here we have a network. Each node is a network now. And you see 5 nodes. All the 5 nodes are, for example, in this case, Erdős-Rényi network. So this node is a network, this node is a network, this node, and the links are dependency between them. Nodes here depends on here and vice versa. And the same for this network, also 5 network. And you see the network of network can be of different structure. Here you see a line, here you see a star, and you see a tree. What comes out, if you do it analytically correct, you found that instead of getting the formula that we get for a single network, this one, which gives you a continuous transition, you get a new formula which is not very different, very little different. What happened? What is the difference between this one and this one? There is a small n comes here in the power. And this n makes a lot of changes. N is the number of networks that you have in the system. If it is a tree-like structure, and if it is full coupling, it means that all nodes in one network depend on all nodes in the other network, you will get this formula mathematically. And now when you solve this formula instead of this one, for n equal 2, you don't get any more a continuous transition, but you get an abrupt transition. You reach a point here where when you want the solution for another smaller, a little smaller p by one node, the system collapses and gets you to this place. And 5 you see here. It means that you can see now how beautiful is the general theory, which includes not only one network, which we knew until 2010, but in 2010 we realized that we have a generalization. You can have not, and it's a natural generalization because, of course, when Erdős-Rényi wrote this formula, he did not put n here because n was 1. He didn't probably know what happens when n is 2. But only in 2000 we realized that you can make it more general by finding n2. And this is we can show that you can generalize it in many ways. This is one way to generalize it. Let me show you what happens during the cascading failure. What happens during the cascading failure? I think I have some time, yes. So what happens during this here, the jump here? During this jump, there is the failures here lead to failures here, lead to failures here, lead to failure, back to failures here. But this happens in a very strange way. I would say in a plateau. This is the number of iterations that you have in the system. How many times you come back to the system? And this is the time. It seems here about 40 times. It means I have 40 cascading failures that come back and forth. And this is what happens from this point to this point. The system first falls dramatically, then it has a plateau, and this plateau later goes down to 0. And it means that you can, if you don't know what is PC, you don't need to do very much mathematics. You have a system, you want to know the critical point, you just measure the number of cascading failure in the system around P, and you will find that there is a maximum around PC, and this maximum is because the plateau it goes to infinite, it diverges when the system is infinite. This is analogous to how to find for a single network PC. We know for a single network, we found PC at this point, we find by the second largest component, which is the maximum. So instead of looking at the second, you look just the number of iterations, and then you see the transition point very easily. Okay, let me just mention that the result that I showed you here was a simplified case where all nodes here depend on all nodes here, and vice versa. but you can have dependency not where all nodes, like in this case, you see some nodes depend, a fraction of nodes. And this is the case where we show when you have a fraction of nodes, if the fraction of nodes that depends is very large, like 0.8, 80% of the nodes in one network depends on the other one, you get abrupt collapse. But when it's very small, Q, the fraction is 10%, you get a continuous. And it's interesting that you can find that there is a critical dependency below which it is continuous and above which it is abrupt. And this is can be solved analytically. Another example is, I will not go into detail because I don't have much time, but let me show you another example of generalization of the network of network. This is another example where you have 5 networks. I'm sorry, 6 networks. Each one is Erdos-Reini with a degree 2.2. The number of dependency, this is the RR network. It means each network depends on, in this case, in 3 networks, on 3 others. And you can see here, each one depends on others. But not only this, we have another parameter Q, which is the fraction of nodes that depends on this node. Q is the fraction. And the formula that we get is this formula for the giant component, how many nodes still can function in this network or network. And you see that it depends on P, the 1 minus P is the fraction of failures. It depends on M, on how many networks this network depends. It depends on K, on the degree of this network, but it depends also on Q, how much dependency I have, what is the fraction of dependency. So this formula is also generalization of the known formula that we have here for single network. Why? Because when I can take the generalization in 2 ways. One way is to take M equals 0. M equals 0, it means that this network does not depend on other networks. So when I substitute here M equals 0, I see all this in brackets goes to 1, this goes to 1, and you see exactly you get the single network result, which was obtained in 1960 by Erdos and Reini. Or I can take Q equals 0. Q equals 0 means that a network does not depend on another. Q equals 0, I get here 1, another 1 here, 2 to the M, and this 2 to the M cancel with this to the M, and then you see again the single network. It means you can generalize, and the generalization leads you to a much more rich phenomena. Instead of having a continuous transition, you can have abrupt transition. You can calculate what is PC for this system, which depends also on Q, on the fraction of dependency, and QC, which is very important. Below this dependency, it's continuous. Above this dependency, it becomes abrupt. So dependency can lead to abrupt collapse, which is not wanted. Abrupt collapse means we are in a very dangerous world. Now the question is, can we mitigate this? After we know that we have a problem. A problem means that in our world we can have abrupt collapse. Can we mitigate? And the answer is we can do it in a very small efforts by mitigation, by decentralization. We can do the mitigation by decentralization. What does it mean, decentralization? It means if I have, for example, here 2 networks, this is the network that is left in the one network, and this is the network, the giant component in this network. If I have only, if I look only at the giant component here and the giant component here, I will not have a functioning network. Now imagine that I do centralization. It means I give a node here, a small fraction of nodes here, another way to connect to the giant component, like another way to have electricity. For example, this node has its own electricity or its own communication, another alternative. It means it's decentralized form. It's not, if it was not like this, it would be decentralized form, it cannot get electricity. But now I give him electricity, I give him communication, I give this one communication also. And then the giant component that can function is much larger. And this we can solve analytically, and this was done in 2000, and we saw that a very small fraction, if you give these components, you can avoid the cascading failure. For example, if you could do it in Italy, you give some of them alternative communication, and they could get alternative power, not using the power grid, you could save the cascading failure, and we can solve it analytically, and we can see that very small, for every Q, you need very small fraction. This was done analytically for both, for scale-free, for Erdős-Rényi network, for scale-free network, and you can see that few percent can lead to avoid the cascading failure and the abrupt collapse. So, and this is a measurement we did on the power grid in USA with a communication system, Erdős-Rényi communication, and you see 1% or 2% is enough to reduce, to make it continuous. Instead of having abrupt, it can be continuous. So decentralization is very important, or reinforced node, you can do change dramatically the fragile of the system. Let me go to the last point. And the last point is localized attack, which is very, very frightening, that you can make a small attack and by itself it will propagate. And we have here two models, two limiting models, how to make dependency links, but both give how to make dependency systems. One is the old one, which we solved in 2012, and the new one, which was in 2017, 18. The old one was like this: you take two lattices, and the dependency is within a distance r. It means these links are dependency, but within a radius r. It means this r is 2. It means this is the same location. This is 2 kilometers or two typical links. Here we take the connectivity not to be fixed, like here the connectivity is 1 unit. Here the connectivity can be from a power law distribution. You see, but the dependency is in the same position. This is more realistic. Dependency is usually in the same position. And if we do this in both cases, what we see, a very similar phase diagram. It means that depending on the distance r here, and depending on the length of the connectivity, we can see how PC changes as a function of zeta, the dependence of connectivity in this field, and dependence of R in this picture. And the picture is very similar. And we have here, if the zeta is small, we have a continuous transition. If R is small, you have a continuous transition. But above a certain value, and this is non-monotonous, you start to have PC and the transition becomes abrupt. It means if you have long-range connectivity or long-range dependency, you start to have abrupt transition. You start to have cascading failure and abrupt transition. And the more interesting part is this question mark, what happens in this place? And I will show you what happens in this place, in this area. This is the phase diagram, and you can see here that you have a metastable regime. A metastable regime, it means that if you have a localized failure here, in this system of a certain radius, above a certain radius, it will propagate above a certain radius, and below the certain radius, it will not propagate. It means that you have a critical radius of damage that will either propagate or not propagate. And this was done in these two papers. We call it metastable because it's stable, but metastable in the sense that if you have a damage, even a zero fraction of damage, it still propagates. I will not, it propagates. You can see here there's a simulation. You can see here that if it's smaller than the radius, the damage did not propagate. If it's bigger, it propagates. And why it propagates? Because of the dependency, because of the connectivity links. You have the damage can go farther. The damage can go farther in both cases. But the phenomena is very similar. Indeed, if we take the power grid in Europe, for example, and we make random attack, it does not propagate. But if we make localized attack, the same number of nodes we fail here, they propagate and propagate. And what is interesting is that the number of nodes needed here in the original doesn't increase with the system size. It means that PC is 0. It means percolation, you can do percolation with PC 1. PC 1. It means that a zero fraction fail and propagates into the system and makes the damage everywhere. So let me summarize, and I will tell you that we can generalize percolation. We can generalize percolation theory instead of single network that we studied in graph theory and in mathematics, and in percolation theory in physics, also mathematics, is only the limited case of n equal 1. It means you take one network. But when you take many networks, you can have, instead of continuous transition, you can abrupt transition. And this abrupt tells you a lot about the cascading failures in this system. A new paradigm, we have abrupt collapse due to cascading failure, in contrast to continuous transition in single networks. Now I showed you that small fraction, zero fraction actually, small fraction of autonomous nodes avoid cascading failure. If I give some fraction randomly, I choose 2% of them to have another way to connect for example, the communication, they are not depending. Some of them do not depend on this one, or do not depend like this one depends on this one. They have their own communication or their own electricity. They have their own electricity. It will change. It means that decentralization leads to a better world. And our world becomes more and more centralized because you need internet everywhere to be connected, for example. And I showed you also that localized attack in spatial network, a zero fraction of failures when PC is 1 lead to full collapse. So some of the papers are here, and I thank you very much for listening. If you have questions, I hope I can answer. Thank you very much, everyone.
Okay, thank you very much, Shlomo. You really went through the history from the 2000s, early 2000s, all the way the last 20 years. Yeah, very nice review of all past work. We have a couple of minutes for questions. Can you read questions or should I read them for you?
Can you read them? I'm not sure I can read because maybe I can do the following. 1 minute. I can go out and then maybe I can read.
Let me read it for you then. When you say abrupt, do you mean discontinuous?
Discontinuous. Analytically, you can show that this is discontinuous. It means when you solve this equation, let me show you. It's a very simple mathematical equation, this one or this one. You can see that below QC it is continuous, and above QC, which depends on AMK, it is abrupt. And you can see it here, very nice. For example, in this formula.
Okay. Are there any other questions?
It is mathematically very clear to see the transition.
We can have some more questions from the audience, from people. Please unmute yourselves and you can ask any question. We have a couple of minutes.
1 minute, maybe I can see. I cannot see the questions.
Hello?
Yes.
I wrote the question in the chat, but I don't know if you can see it. When it is about having many layers and by reinforcing some of the nodes, you can avoid the huge cascades, as you explained. Does it depend on which nodes are you going to reinforce? Let's see.
Oh, this is a very good question. What we solved was the case when you do it randomly even. But of course, you can find what are the best nodes. This can be another paper to do. And if you find the best node, you may get even better results because, but this is a question of research. And I know that people are doing it now, studying which node are best to reinforce. And it's not, here we did it, we solved it analytically for random. I mean, I take randomly nodes and choose them to reinforce to give them alternative. But if you do it, of course, more efficiently, maybe you can reduce the concentration by some factor.
Okay, thank you very much, and thank you for your talk.
Yeah, thank you.
I have a question in the chat. Let me read it out.
Yes, please.
Are these transitions abrupt even when the connected networks are of different topologies?
Oh, very good. Yeah, of course. The abruptly occurs almost in any topologies, even if they are different topologies. Okay. And usually, even I will tell you, if you have one is small degree and the other is large degree, so the abrupt collapse happens when the small degree already collapse, it collapses the other one because of the dependency. So it means the weaker network always dominate the abrupt collapse when to occur. If it's, it means that if you make one weak and one strong, the strong will not influence because because of the dependency, it will break when the weaker one breaks. But we studied simple cases just because we wanted to have beautiful formulas like this one, and beautiful formula like this one, which shows that indeed it is a generalization of this one, because you see the n, small n, tells you how many networks. So we simplify the question, but of course it's a very rich problem, and people are doing now much more rigorous and more complex structures.
Okay, thank you.
Another question that I see, Shlomo, is what happens if there is a hierarchy in the model? Does the system become more fragile?
That's a good question. This was studied by Sarai, I think, from USA, and she found a dependency between networks which are hierarchical. And also, I mean, hierarchical means that you have communities of communities and communities. So it depends very much where you put where the dependency occurs, and it depends on the structure, but they also have a similar phenomena of transitions. And but I want to say something, that this question, what you say, Panos, is very important, because if you have infrastructure, usually they are hierarchical, because cities are more dense, and between cities are less dense. So in the same city, you have more dependency and more connectivity, but another city, you have also high connectivity and dependency, but the two cities, their dependency is very low and the connectivity is very low. So one needs to study also systems which are not homogeneous, like I studied here, but also they are heterogeneous in the sense they have communities, also communities of different sizes. So it's open to the question, and many open questions appear here. Thank you, Panos.
Yeah, there's a lot of other questions here, but I think we don't have that much extra time. You may want to note these questions that are written on your chat, and somehow
can you copy them and send it to me? I don't know. Yeah, but I don't know. I don't know how to see it. Somehow I cannot see it. I don't know.
You just click on chat. You just click on chat. That will stay there.
Yeah,
so
I know.
It will
later I can click on chat.
Close
if I see some question, I will answer.
Your presentation. Okay. On the bottom, there is a share screen, and next to it is chat. Just left to it on share screen. So when you stop your sharing screen, then you can view it.
Only when I stop the share screen.
Discuss later. But we have to stop now.
I can send some answers. Okay, I will put some answers.
We have to move on. Sorry.
Thank you very much.
It's interesting talk. I know there's a lot of discussion, a lot of people interested in going over these ideas, but we have to stop. So we stop now and we go to a break for about 10 minutes, and we start in 13:35, which is like 7 or 8 minutes from now, with the parallel session 3. Thank you very much, Shlomo.
Thank you, everyone, and thank you, Panos.
Okay.
Bye-bye.
Bye-bye.